today's video. Today's video is a quick introduction to section A1 of the IBSL Physics curriculum, which is kinematics. Kinematics, as I found, is a unit that is foundational. It is the simplest unit, yet it teaches you most of the skills that you will be using throughout your entire physics career. And I've basically found that it doesn't get as much attention as it deserves since I'm making this video. So let's start by defining kinematics. Kinematics is a subsection of mechanics which deals purely with motion. So this subsection does not deal with forces, which are the cause of motion, which is the next unit, A2. Now that we have defined kinematics, we can move on. So let's talk about how we describe motion in kinematics. We describe motion in kinematics by using this thing called a vector. Now, if you already know what a vector is, you can skip a few minutes ahead. There'll probably be a timestamp, as right now I'm going to be describing what vectors are. Alright, so anyways, vectors are essentially values that have both a magnitude, aka size, and a direction. And these values are usually used to describe objects in motion, whether it be how far they have moved away from their original position or in which direction they are moving in, aka displacement and velocity. Now, the magnitude of a vector is self-explanatory. It's the numeric value assigned to the vector. So let's just say there's an object that has a velocity of 5 meters per second. The magnitude of the vector will be 5 meters per second. However, the direction is a bit more complicated. Vectors are mostly always represented on a Cartesian plane. Before, before determining the heading of the vector, we need to first figure out visually if the vector will be positive or negative. We do this by defining which directions are going to be positive or negative. Now, what do I mean by that? Both the x-axis and the y-axis are split into by each other at the origin. One half of each axis has to be positive and the other has to be negative. So, to determine the vector's relation to the origin, usually like on a regular Cartesian plane, the right side of the x-axis and the top side of the y-axis will be positive. Alright, now that we got that out of the way, we can move on to the two ways of expressing headings. The first method is by using angles. The most common method of doing this is to find the angle between the vector and the y-axis. Note that you would start from the y-axis and go in a clockwise direction until you reach the vector in order to find your angle, which in this example is 60 degrees. Also note that there are other ways of denoting the angles and direction, as for example, in some places, students are taught to draw their Cartesian planes like a compass, like so, and then you would denote the angle in relation to north, south, east, and west, as well as the direction in which it is deviating to. So this angle could be rewritten as this using this format, where in square brackets you first put the direction which is closest to the vector, in this case that will be east, then the angle between that direction and the vector, which is 30 degrees, and then you would denote in which direction it is deviating to, which in this case it's deviating into the northern direction. Hence, we write n at the end. Now, the second way of defining vectors is by finding the x and y components of the vector. So, for example, let's take this vector that makes a 30-degree angle with the x-axis. Now, we can draw two imaginary lines, like so, from the origin, and make a right angle triangle. These two lines are now what we call the x component, or the horizontal component, and the y, or vertical component of the vector. And these vectors have a more common term. They are the unit vectors, as they are the two vectors that sum up together to make the resultant or original vector. Now we can find the magnitudes of these vectors by using SOHCAHTOA, which is sine, cosine, and tangent. So for example, to find the y component of this vector, we would set up an equation like so, and then isolate for the unknown to get your y component. Now I know that that was a lot, but understanding vectors is really important for solving most questions in kinematics and physics in general. So now that we got that out of the way, we can move on to the equations that you need to know. The very first equation that you will be taught, when the simplest equation you will be taught, is the equation for velocity, where velocity, or v, is equal to displacement divided by time. Notice that I use displacement rather than distance in this equation, as these two terms are not the same thing in physics. Displacement measures your change in position, which is depicted as a straight line drawn between your origin point and your final position. Meanwhile, distance is the total length that you traveled, which is not necessarily equal to the displacement. It will never be less than the displacement, but it will almost never be equal to the displacement at the same time. So in order to measure speed, you'd use the same exact equation, which is velocity equals displacement divided by time, but you will replace velocity with speed and displacement with distance. And that's it. Let's do a simple example using this equation. Pause the video right now if you want to do this problem on your own. Alright, so essentially this problem is giving us two values. That is the velocity of our object, which is 5 meters per second, and the amount of time that is in motion, which is 20 seconds. And it's asking us to find its displacement, or the s value. So we can start by writing out our equation, which is v equals s displacement divided by t. Now that we have this equation, we can isolate for displacement, yes, by multiplying both sides by t to give us the equation s equals t times v, or s equals vt. Then after that, we can substitute our velocity value and the time period, which is 20 seconds, into our equation. We then multiply these two values to get our displacement, which is 100 meters per second. The next concept that I'll cover is acceleration. Acceleration, by its technical definition, is the change in velocity over time. So what you do to find acceleration of an object is by taking the change in velocity and dividing it by the amount of time that it took to undergo this change. And acceleration is really important in kinematics specifically, as it's pretty much in every equation. The equations which I have introduced thus far are pretty rudimentary, and it can solve more difficult problems. However, the process for solving these problems would be pretty complicated, which is why some smart people came up with the four kinematic equations, which you can see on the screen right now. We have discussed or mentioned almost all of the variables used in these equations, except for one, that is u. In physics, in kinematics specifically, we deal with changing velocities, so most equations will essentially denote this using u, which is the initial velocity, and v, which is the final velocity. Each of these four equations has its own use case and can easily be derived. I'll explain what each equation is trying to say. For example, what the first equation is saying is that if we add the initial and final velocities and divide that by 2, or take the average of the two velocities, and then multiply that by the time, you will get the displacement. It is essentially the same equation that I introduced at the start of the video, v equals s divided by t. Moving on, the second equation is telling us how to find the final velocity if we have the time period, the acceleration, and the initial velocity. Acceleration is the rate at which velocity changes per second. So if we multiply the acceleration by the amount of time in seconds, we will get the change in velocity, which can then be added on to the initial velocity to get the final velocity. Nothing too complicated, right? The third equation is where things start to get more complicated. This equation is used to find displacement when you know everything except for the final velocity. Now, there's no really intuitive way of explaining this equation, so it's easier to derive it. As we know, average velocity is equal to distance divided by time. Now, average velocity can also equal to the sum of the initial and final velocities divided by 2. We can equate these two expressions to get the following equation. Now comes the fun part. We take the second kinematic equation, which is this one, and we substitute it for the final velocity. After that, you can simplify the expression to get u plus 1 half at equals s divided by t. Now, if we isolate for displacement, we get our final equation, which is ut plus 1 half at squared equals displacement. The fourth and final kinematic equation is used when you have all of the data other than time. And the equation is similar to the third in the fact that you have to derive the equation in order to understand it. We can start to derive this equation by using the second kinematic equation and isolating for time like so. Then we take the third kinematic equation and substitute t for the first equation to get this. Then if you expand this equation, you get this expression, where then by adding both of these fractions, you'll get this expression, where you can then isolate for v squared to get our final kinematic equation. Alrighty, so I know that that was a lot, but generally not many people are going to ask you of how to derive these specific equations. But it's still useful to know because it's important to understand where these equations actually came from if you want to get a level 7 in physics. And also, on many IB exams, deriving specific equations is a genuinely pretty common question that can come up on your exams. They came up on my exams, in fact. However, I doubt that anyone will ask you to derive these specific equations, but you should still know how to do it. Okay, to end this video off, let's do one practice problem to just understand how and when to use these equations. Let's take this equal question for example. This is what we call a projectile motion question, where there is an object being fired at an angle and which comes back down to the ground under the force or the acceleration of gravity. Now this question is specifically asking us to find the horizontal distance that the object flew. Now how would we go about solving this problem? Let's first look at what the question gave us. And by the way, if you want to solve this question by yourself, feel free to pause your video and come back later. Alright, so the question says that the initial velocity is 20 meters per second, plus that the projectile was fired at an angle of 20 degrees in relation to the ground. Then, the question also specifies that the vertical acceleration is negative 10 meters per second, or 10 meters per second in the downward direction. Note that gravitational acceleration is denoted by the variable g rather than a. So, to solve this question, we first have to get the unit vectors of the x and y components. This is why I was talking about vectors at the beginning of the video. So, we do this by taking our initial velocity, and then we can use SOHCAHTOA, as I demonstrated in the previous portion of this video, to get these two expressions, which when solved yields the x and y components of the velocity, which are these values, which you can see on the screen right now. Now that we have these two values, we can make several other deductions. First of all is the fact that ux, remains constant until the ball hits the ground. Since there is no horizontal acceleration acting on the ball, so the velocity will remain the same. Only the uy changes since it is acted upon by the gravitational acceleration. Therefore, the horizontal displacement is equivalent to ux times the amount of time that the ball was flying, as ux remains constant, so we don't have to do anything else. We can similarly deduce that the vertical displacement is zero, since there is no change in elevation, meaning that when the ball hits the ground, it will have the same y coordinates or elevation as when it started flying. Alright, now that we have all of these deductions, we can introduce one of the kinematic equations. This one to be precise, the one you can see on the screen, where the displacement in the y direction is equivalent to the initial y component of the velocity times time plus one half of the gravitational acceleration times the time squared. We can substitute for the vertical displacement the initial vertical velocity and the gravitational acceleration, like so, which simplifies to this formula. Now we have a quadratic equation, so we must use the quadratic formula in order to find the possible values of t. Alright, so if you have used the quadratic formula correctly, you should have gotten two values of t, that being t equals 0 and t equals 1.37 seconds. We will reject the t equals 0 answer since t cannot be 0 in the current context. Instead, we'll keep t as 1.37 seconds. Now that we have both ux and t, we can find the horizontal displacement using our initial equation. If we substitute for the horizontal velocity and the time period, and multiply those two values together, we will get the horizontal displacement, which is 25.7 meters per second.